Suppose now we are given a function, right? This is our function f of x, and we are also given, or we want to find the slope of the tangent line that is touching at that particular point only. So we have a line. If this line is tangent, is touching at that point only. So we want to find the slope of this line that is only touching this curve at this point. And the only information that we have about this line is the information that we are getting from that particular point, because the function f, we will actually have information on this function f. So if we wanted to find this coordinate here, we know that the x value is just x and the y value is going to be f of x. So the information we can deduce for this line, it can only be found from that particular point, which is on this curve. So let's first recap a little bit. This is a straight line, and when you are actually trying to look for the slope of a straight line, you know that you need to find 2 points, and to find the slope is going to be y2 minus y1 divided by x2 minus x1. So the slope is just can be found using this equation here. And if the points are given, you use that. If you are given a function and the x values, you just take this value and you plug it in some f of x to get the y2, and to get y1 you take x1 and you plug it in f to get the y1, and then you divide by x2 minus x1. So for points, you use that. If you're given a function and the x values, you use this particular function. But both these two things are actually telling us that you need 2 points to actually find the slope of a straight line. One must have x1 and y1, and the other point must have x2 and y2. That's actually those 2 points that we actually need. Now, if we only have 1 point in this line, then we cannot actually find the slope of that line. We can only approximate it. So how can we approximate the slope of this? Because we only have information on this particular function here, we need to find the second point on this particular function, so that that point can help us to get the slope of the line that is passing through 1 point in this function and that point, so that we end up having 2 points. What I am actually saying here is this: we need to pick a point somewhere here. Let's say I pick a point somewhere there, and this point here is somewhere here. So how do we find out this point here on the x-axis? So we want the difference between x and that point to be equal to some value h here, so that this one here is going to be x plus this h. We get that point there, right? Because to move from here, the length from of this line is actually h. So I already know that the length from the origin up to here is x. So the length from here to here is h. So to get the value here, I just need to add x and h to actually get that. And actually the output of this function, the output of this point, or the image of this point here, is actually going to be not that hard, because you take this value here, this x value, and you plug into this function, so that you end up having f of x plus h. So that is the output. And the third thing that you do, you need to draw a line here that is going to pass through this point and that point. And also notice now that we're actually having 2 points, this point and that point. And this one, we're gonna call it, this line here, we're gonna call it G. And if you look now at the slope of the line G, you can see that we will actually have y2 we will actually going to have y2 minus y1 divided by x2 minus x1. And this point here is the one that we call our x1, and this point here is the one that we'll call our x2, and this one, since it's x1, this output here is gonna be our y1. So our y1 is equal to this, and then since our x2 is this, our y2 is going to be that point there. So this one now is going to end up being f of x plus h minus f of x all over if you look into this, our x2 is going to be x plus h, so I have x plus h, and then our x1 is actually going to be actually x. Now take a look into this, that we can actually simplify this whole thing and say we have f of x plus h minus f of x, and then divide this whole thing by x, and x will go away and we are left with actually h. So we have found the slope of this line here. Now the question is, can we use this slope of this line to approximate the slope of this line t here? The answer is actually a big no, because you can see that this line and that line are not parallel at all, and there's a huge gap between these two lines, which means that the slope of this line and the slope of that line are way too different when you are actually comparing them. So we cannot use the slope of this line to actually approximate the slope of this line here. Now we have actually found the slope of this line. Now the question is, what can we actually do to this line such that its slope is actually a good approximation of this line t here? Yes, we do need 2 points to actually find the slope. We have found the slope of this particular line here. So the next thing that we actually need to do here, we actually need to make sure that we want to find this line, or want to make sure that this line here is so close to this line such that we cannot see the difference between them. In other words, this line in our in the eyes and also using a computer is actually overlapping with that line, so that the difference cannot be seen, even though the difference is still there. But we wanted to make sure that the difference is actually not seen to actually approximate the slope of this line with that line. So what do we actually do? In order for this line here to overlap with that line, what we need to do, we need to push this line up. And when we are pushing this line up, but we fix that point and it's not going anywhere, but we are only pushing this line to go this way. And now, how can we make sure that we push this line so that it overlaps with that line, but still we have a point, a point on this function here? So as I keep pushing this line, you will find out that this point here will not be here, will actually be moving and moving this side here. To make this thing so short here is this: if let's say now I pick another point somewhere here, a point somewhere here on this function, right, such that now I pick another point such that now my x2 here is somewhere here. So my x2, which is equal to x plus h, now is somewhere here. Take note of this. If I pick a point now so close to this point, this point is somewhere there, but this point is still on the curve, what will actually happen now is that this line here will be pushed as much as we actually wanted to here, and it's gonna pass through this point. Can you see that it's actually passing through those 2 points here? It's actually passing through those points here, and now this function has actually moved there, and this line here is still our G. And this line here, as we pushed it to be there, this point actually moved to be in this position here. Now, if you actually look into this thing here, this line here was actually pushed this way. As we keep pushing this side, this one moved and this one moved, but here it was fixed. But we did not push it so much that this one does not touch the curve at the other point here. We pushed it so nicely that we still have another point that is so close here. Now, if you look at this H here, this H now, because H is actually the difference between X and the new point, our H now is somewhere there. So we have our H here. So this H here has been actually reduced and is actually reduced. In other words, this H is actually keep moving and is becoming closer and closer to 0. Let me repeat what I'm saying here. We had this point here, but now when I have this point and I'm drawing this red line here, which was G, I found out actually there is a huge gap between the black line and the red line. So this cannot be a good approximation. So we had this. So we decided to choose a new point that is so close to the given point X here. So if you look into this point here, and then I drew a line that is going to pass through the original point and this new point here. And this line is the blue line. In other words, to get this blue line, I pushed this red line here, but I fixed it there in such a way that I still have another point at this particular position. Now, while I keep pushing this, the difference between this line here and the red line, it actually was reduced. In other words, this one was actually moving up until it became this blue line here. Now, to make sure that this line here is actually so close to this and is overlapping, I pick a point that is so close to this point that even a computer is not going to actually see the difference here. So in order for me to pick a point that is so close here, I actually need this H to be actually approximately equal to 0,0000000. I have so many zeros and then I have 1 in the end. So many zeros, not this one, these were finite. So many zeros so that the calculator and also the computer is not going to find out this H, and it's only gonna find out that this H is just a 0. But we know that this point is so close here. It's not the same because I need 2 points to find the slope of the line. So I pick a point that is so close, right? In other words, this H is so close to 0, but it's not 0, but it's close to 0. So the difference between X and this point here is close to 0. In other words, these points are so close here, so that these points are so close there, so that I can get what I'm looking for. Now, how do I say that mathematically, that I was picking a point so close here so that this here is actually a good approximation of the slope of the tangent line? So the slope now of the tangent line, I'm going to place a T here, is actually going to be found, or we're going to get a good approximation if we are actually getting a point that is so close. To say that I picked a point that is so close, I'm just saying the limit. But now this here is determined by H. So if this H is so small here, then H is so small in such that H is actually getting closer and closer to 0, right? H is getting closer and closer to 0 here, then this point is actually going to be closer. So also the same thing here, the limit as H approaches 0, and also the same thing here, we have the limit as H approaches as 0 here. What this is actually saying is that to get a good approximation of this line here, we actually just need to make sure that this H here is close to 0. But take note now that usually to say the slope of the tangent line, we usually say that f prime of x, this is the slope of the tangent line at point x, where x is just x. So at any point on the curve, we usually denote it like this, and we say that this is the limit as h approaches 0 of f of x plus h minus f of x divided by h. So this h is getting closer and closer to 0 because that difference, we don't want the calculator to actually get to see it, or the computer. Now, I want to explain why am I using equality here. If we can make the difference between these 2 points so close that even our computer cannot pick it up, then because we cannot see, that difference cannot really be seen, we can actually see that the difference between the actual slope and this approximation is actually not going to be that much. That is why that when you are calculating it, you still gonna get the exact same thing, because the difference is going to be 0.000000. Maybe you will end up having million zeros or trillion zeros before 1 to actually see the difference, and even the computer cannot see it. So this one is not only an approximation, is the exact slope of actually the tangent line that is touching the curve at point x. And this equation here, we usually call it the first principle of calculus. So now we have we have discovered so many things. We'll take some examples here. I want you to take note of this, that to find the slope of the line, we know that we have y2 minus y1 over x2 minus x1. We dealt with that, and we also went along to say that the slope can also be found by saying I have f of x2 minus f of x1 and then divided by x2 minus x1. We dealt with that, and we also went along and we said that this one here is when we are given the points, and this one here is when you are given only the x values and the function, and then the next one is when you are actually given the function and the difference between points, not the actual points. So this one we said it was f of x plus delta x minus f of x all over delta x. So that was another way to find the slope. So this one was just a slope of the line. Now, when we were actually finding the slope of the tangent line, we said that we can find the slope of the tangent line at any point A by just saying that we want the limit as x approaches A of f of x minus f of A all over x minus a. We also talked about this, and the good thing, I'm not sure whether it's good or bad, some of the students actually did not want to actually did not really like this, like they were jumping for the first principle. But you also need to know this, that actually the slope of the tangent line at point A given the function x can be found using this function here. And now we just discovered that actually the slope of the tangent line at point A is just the same as the limit as h approaches 0 of f of a plus h minus f of a all over h. So that's also another way to actually look into this slope. So we have different definitions of actually saying the same thing, this one and that one. This is the exact slope of the tangent line, and this one is just the slopes of the line. So we have now the first principle. Let us take some examples on this. But before we do that, I want us to actually look at the definition here. There's also another definition that I want us to look at here. Use black. Here we have a definition. So by definition we say that if y is equal to f of x, right, then f prime of x is just equal to the limit as x not x, as h approaches 0 of f of x plus h minus f of x all over h is called the first principle of calculus. Of the first principle is just the first principle, but it's first principle of calculus, given that the limit, so this limit, given that this limit, the limit exists, right? So that's what is actually happening. This one here is called that. Now if let's say now we are using this is supposed to be Leibniz notation, we actually end up saying the same thing, that instead of using f prime, we usually use y prime is the same as just dy dx, and this is just still the same as h approaches 0 of f of x plus h minus f of x all over h. The main thing behind this notation is that Leibniz is also one of the greatest mathematicians and philosophers we actually had that actually contributed a lot in mathematics, especially when it comes to calculus and statistics. So when he was actually studying calculus, which was actually independent from the work that was done by Newton when he was doing mechanics, you will find out actually that he found so many useful principles and useful and applicable studies when it comes, and also principles of calculus and also in stats. So he was using this notation when he was doing his studies, so we sometimes use this to honor his work, because he have done a lot of very, very, very significant work when it comes to mathematics and also statistics. So another definition would be this is also important definition. A function, we have a function y is equal to f of x is said, f of x is said to be differentiable. So we say that it is differentiable at x is equal to a if f prime of a exists, right? So basically here, if let's say you can find f prime of x to be equal to some function, and when you are looking at the domain of that derivative of the function that you got, you look at the domain, you find out that actually this a here is actually in the domain of that derivative there. Then we say that f prime of x is actually, or this function here is differentiable at that particular point. Alternatively, if you have found this derivative, right, and then you got some function, and when you are plugging in a, you get some value, then we say that function is differentiable at that particular function, but at that particular point. But if when you are plugging in a at f prime of x and you are getting undefined, then this function here is not differentiable at that point. We want its derivative to be defined, right? Now, we'll take some examples here, a few examples. And also another thing that I want to talk about here is this thing here that I keep saying a lot, the derivative. What is the meaning of a derivative? A derivative is something that comes from something else. For instance, if let's say you have an orange or an apple. Suppose you have an apple, and now you create a juice out of this 100% juice. So you will end up realizing actually that in order for us to have this juice, we needed to have an apple, or we needed to have an orange here. So this juice here actually comes from this apple here. Without this apple, there was no orange. Without this apple, there was no juice. So this juice here came from that apple. So since this one comes from that, we say that this juice here is a derivative of that apple. So in terms of functions here, you can see that we were not going to get the slope of this tangent line without this function here. So the slope of this tangent line is actually the derivative of that because it comes from this function here. So all these things that we are getting f prime of x, they are depending on the function f of x. So these are actually the derivatives of the original function. So when I'm saying that f prime of x, the derivative of f of x, I am actually saying that this is coming from that particular function, and I am actually referring to the first principle, right? Now, if you look into this here, you will find out that actually this function here is said to be differentiable if this one exists, or in other words, if a is actually in the domain. If a is actually I'm gonna use this one here. What it is saying, a is in the domain of f prime of x. So you need to have a domain, or you need to have this function, find the domain. If a is part of the domain, then it's fine. Or you need to find f prime of x and then plug in a. If you are getting a value, then f is differentiable at that particular point. Now, the second thing here is this. The function, let me go back here. Okay, the function y is equal to f of x is said to be differentiable. Is said to be differentiable on an open interval. It's said to be differentiable on an open interval AB, or we can say, let me say, or from a up to positive infinity, or from negative infinity to a, or I can say that from negative infinity to positive infinity if it is differentiable. If it is differentiable at every point in the interval. So what this thing is saying, that this function is differentiable on this interval, or this one, or that one, or that one, if and only if this interval is part of the domain of f prime of x, or this interval is part of the domain of f prime of x, or this one is part of the domain. So what is actually important here is actually, once you get this function, find its domain. If we are asking, is it differentiable at a, is a part of the domain of that? That's simple. If we're asking, is it differentiable on this interval, we're actually asking you that, is this interval part of the domain of that? That's what this whole thing is actually saying. Let us take some examples here. These are the nice examples that I actually have. I have these examples here. The first one is saying here, find the formula of f prime of x using the first principle. Right. So my A here is saying that I have f of x is equal to x, and then my B here is saying that I have f of x is equal to x squared, and then my C is saying f of x is equal to x plus square root x, and then D here is saying that we actually have f of x is equal to the absolute value of x. And then number 2, what we actually wanted to find here, where are the functions f in question 1 differentiable. Differentiable. Where are they differentiable? In other words, find the derivative of this, 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 and actually find the domain of each of these things here. Let us actually look into this thing here. Before I move forward here, I want you to also remember that the absolute value is x if x is greater or equal to 0, and minus x if x is less than 0. That's what I want you to find out. Let's look at the solutions then and move forward. Solutions. Let's look at number 1a. I'm just going to look at A. So what we're actually going to do here, we'll find the derivative, find the domain, and then at the same time talk about differentiability. So let's look at this one here. We had our f of x, which was just equal to x. Now, if you look at f prime of x, we know that is always going to be the limit as h approaches 0. Once you leave the limit here, you're supposed to not get any marks because you don't know what you are really doing. So this limit here must always be there, because to find this, remember that we're making our h to be so small so that we can actually make sure that the outputs are so close to each other. So without this thing here, you don't know what you are doing. You're supposed to get a 0 marks. So make sure that it is always there so that you don't lose marks unnecessarily, because this is way too easy. And this one is going to be f of x plus h minus f of x divided by h. So all we need to do, we need to plug in here. The limit is still there as h approaches 0. You only drop this when you are plugging in. So here, I'm going to plug in s plus h where there is x. So I'm going to go there. So f of h is going to be x plus h. So in the value of x here, I'm going to plug in x plus h minus, what is f of x as it is? So I'm going to say minus x all over, and then I'm going to divide it by h. This is the same as the limit as x approaches 0. No, this is not x, this is h. If I'm writing x approaches 0, which means I also need to get a 0. That's how this thing is. But either way, don't make the mistake that I did. Always have this this h here. So I have this, which is just x. So I have x minus plus h. So I have x, which is positive, and x. So I end up being left with only h here, because x and x will go away, and I'm left with h over h. And if you remember, when we were actually doing limits here, we said that if I were to plug in 0 here and 0 here, I will end up having 0 over 0, which means I need to factorize and cancel out the common factor. So the common factor here is h and h, so I have the limit as h approaches 0 of 1 here. The limit of a constant is just that constant. So you drop the limit because now you are plugging in. So that's when you actually drop the limit here. So basically, f prime of x is just equal to 1, which means that the slope of the tangent line touching this curve at point x is just equal to a 1. Now, if you were to notice here, whenever I have y is equal to a 1, this function here looks something nice like this. If y is equal to 1, it's always going to pass like this. So all the values of x have an output. All the value, and this goes from to negative infinity and to positive infinity. Whenever I pick a value here, there is an output. All of them have an output. In other words, the domain of this function here is just x is an element of real numbers because I can always plug in everything. So the domain of f prime of x is just going to be x is an element of real numbers. What that's supposed to mean? This one is saying that f is differentiable everywhere. In other words, whenever I pick any value of x, this function has a derivative, or the tangent line is going to be 1, or the gradient of the line y is equal to x is just 1 at every point. So that is actually what this thing is saying, differentiable everywhere. Let's look now at number b. What was b saying? B was saying f of x was equal to x squared, which means that f prime of x, which is the same as the limit as x approaches as h approaches 0 of f of x plus h minus f of x all over h. So this is going to be, the limit still needs to be there, because if it's not there, you start to lose your marks. So I'm going to plug in x plus h in the value of x in this function here. So I will end up having x plus h, and then I square it up, and then I take that function as it is. So I will have x squared all over h. And if you look into this, this is going to be the limit as h approaches 0. And then I'm going to expand this whole thing here. Why am I expanding this whole thing here? Is because if I am plugging in h here, I will end up having x plus 0, which is just x squared. And x squared minus x squared is going to be 0. And then I'm plugging in a 0 here, I will get a 0 over 0. So because I have a 0 over 0, something needed to be cancelled out. So I need to first expand this and see what am I going to get. And maybe there will be something that can be cancelled out. So here, this x plus h squared is just the same as x squared, so we'll end up having x squared, and then x times h is going to be xh times 2, so I will end up having plus 2xh, and then plus h squared, so I'm gonna end up plus h squared. And then when it comes to this one here, I'm just gonna leave it as it is, and then I divide by h. Or you can expand this on the side and say I have x plus h and x plus h, and then I multiply this with that, I get x squared, and then I multiply this with that, I get plus xh, I multiply this with that, I get plus xh, and then I multiply this one with that, I get plus h squared. So this whole thing is going to be x squared plus this one, and that one is the same, 2xh plus h squared, which is just the same as that, and then minus x squared. I have x squared minus x squared, this one and that will go away, and now you are left with the limit as h approaches 0 of 2xh plus h squared all over h, because this one and that one goes away. If I am plugging in h here, this whole thing will be 0. Plugging h here, this will be 0. 0 plus 0 is 0. Plugging a 0 here, we will end up having a 0. So I will have 0 over 0. In order to remove that, I need to factorize something. There are marks actually for just factorizing. Did you know that? That I can just factorize h and end up having 2x plus h and get some marks. You cancel this one and that one. you are actually getting more marks, and you are passing test 2 or whatever you are passing. But I mean, that's what happens when you factorize things, you get marks. This and that is gone, and now you are left with x plus h. You are not dropping this thing here until you start to plug in. Now we are going to plug in, so we drop the limit. So when we are plugging in, because now what we are basically saying now, we are saying that we are taking the value that is so close to 0, 0.0000000, such that the calculator and the computer cannot find out what you are doing. In other words, the calculator, whatever that value is going to round off to actually 0. So we can actually plug in, and we say that we have 2x plus, there is no h here, so we are only plugging in the value of h. So there is no h here, so we will only plug here plus 0, which is just equal to 2x. What this actually means, it means that f prime of x is just equal to 2x. In other words, the slope of the tangent line touching the curve f at x is just 2x. Right. Now that we have that, you can see now what is the domain of this function. The domain of the function f prime of x, because this function is defined everywhere, so x is an element of real numbers, which means that f is differentiable everywhere. So that's what is important here. So it is differentiable everywhere. That's what is important here. Let's talk now about number C. Number C is saying we have f of x, and f of x is just equal to x plus the square root of x. Of course, when you look into this, when you want to find f prime of x, this is simply going to be the limit as h approaches 0 of f of x plus h minus f of x. If you don't write this one here, we don't know if you know the first principle, so you must always write it unless you are happy to lose 1 mark for this whole thing. So always make sure that you write this as it is. You forget the limit, you're not gonna get any mark, because this needs, everything need to follow from this. So if you don't know this whole thing, I just assume, or anyone else assume, that you don't know what you are doing next, because this is the definition of actually the first principle. So when we're saying use the first principle, first state, make sure that you know what the first principle is. And then now here, this is just gonna be the limit as h approaches 0 of this here. Wherever I see x, I'm gonna plug in x plus h in f. So here I will end up having x plus h plus the square root here, where there is x, is going to be x plus h here, minus, what is the f of x? F of x is just x plus the square root of x. So that was our f of x. Please make sure you put these brackets here so that you don't make a mistake of only separating this and you are not separating that. And then you divide this whole thing by h. And then of course, we will continue to simplify this limit here. We know how to deal with limits, so that I have x plus h, and then I have plus square root of x plus h, minus times a positive is going to be a minus times a positive is going to be a minus, and you divide this whole thing by h. And if you look into this x and this x will go away, this x and this x go away, but the h will remain there. So I end up having the limit as h approaches 0 of h plus the square root of x plus h minus square root of x all over h. And what is nice about this whole thing here, you can see actually that I have some two functions here. The first one is going to be h. I'm just gonna say this, I'm gonna divide this by h plus the square root of x plus h minus square root of x all over h. Why am I actually splitting these two? First of all, I can do that because I can treat this as one term and this one as one term. And if I'm looking at this, the common denominator here is h, so I can take the common denominator to be h, and then h divided by h is just h, and then times h I get that h, and then h divided by h I get a 1, and then 1 times this whole thing is that, so it is fine. And then secondly, the reason I am doing that, I want to make sure that I can cancel out that h with that h, and also this one here, I already know the limit of this because we did it above. That's why I'm actually splitting this, so that I can deal with this separately and also deal with that separately. That is why I am actually doing that. And then secondly, now I can move on and say the limit as h approaches 0. Take note of this. I know the limit of this, and the limit of this will exist. Why? Because if I'm plugging in a 0 here, I know that I will end up having the square root of x minus the square root of x, which is 0, divided by, if I'm plugging a 0 here, so I will end up having a 0 over 0. So there is something that can be done here. I also get a 0 over 0. There is something that can be done there. So I know this limit will exist, and that limit needs to be will exist. So all I need to do now, I can split this limit and deal with them separately. So I'll end up having the limit as h approaches 0 of the square root of x plus h minus square root of x all over h. And then now if I plug in a 0 here and plug in a 0, I get a 0 over 0, which means now I can just cancel the common factor to get the limit as h approaches 0 of 1 plus the limit as h approaches 0 of the square root of x plus h minus the square root of x all over h. Take note of this here, that I have this h that I want to cancel out, but is inside the root, so I need to remove this root here so that I can cancel this. So in order for me to remove this root, the root is in the numerator, so I have this term and that term. I need to rationalize the numerator, not the denominator, because this h is exposed. That is the h that is hidden. That is why I need to rationalize the numerator. So I'll end up having the square root of x plus h, and then to rationalize this, we had a minus here, so you must have a plus here, and then we have an x all over. This thing was not part of this, so I need to divide by it again. So I will have the square root of x plus h plus square root of x. And looking here, the limit of a constant is always that constant. Let me proceed now and focus on this limit here. And of course, this h is already exposed here, so I'm not going to simplify the denominator. I'm only going to simplify the numerator because I am interested in that h and I want to cancel it. So this one, I will leave it as it is. So I will end up having an h times the square root x plus h plus the square root of x. I'm not going to simplify this because h is already exposed. This is the h that was giving us a problem in the denominator, so I don't want to simplify it. I want to cancel it. And then when it comes into the numerator, that's where I have to simplify because there is that h that was hidden there. So this part times this part here is going to be the square root of x plus h squared. And then this part here times that part is going to be plus the square root of x times the square root of x plus h, and this part times that part, we can see that we have a negative and a positive, so we have a minus square root x times the square root of x plus h, and this part here times that part, I have a negative and a negative, so I'll end up having a negative, and the square root times the square root, I'll end up having the square root of x squared. And of course, I still have a 1 here. You forget this one, you forget your marks, so make sure that you don't forget that 1 there. And then here, this part and that part is the same, except the signs are actually opposite, so this is going to be taken out by that. And this part here, this square will remove this square root here, and we'll end up having x plus h. This one will go away, this one will go away, and then we'll end up having a minus, and then this square and that square root will cancel each other, and we're just gonna be left with minus x, and all over I have an h. I am not going to simplify this because this h is waiting for that h that was inside there to cancel it. So this one here is still going to be x plus h plus square root x. And then as we keep continuing here, you can notice that this x and this x are the same, except this one is positive and negative. So these two are going to cancel each other, and we are left with this 1 plus the limit as h approaches 0 of h in the numerator divided by h times the square root of x plus h plus square root of x. And then if you look carefully into this, I don't want to forget this one because I end up forgetting some marks if I do so. And then here, this h and this h will cancel out, and now you'll be left with the limit as h approaches 0 of 1 over the square root of x plus h plus square root x. And now we'll try and see if we can plug in and get some values. I still have a 1 here. When I'm plugging in a 0 here, I will end up having a 1 divided by square root of x plus a 0 and then plus square root of x. Take note that when I'm plugging in, I leave the limit. That's when you actually leave the limit, not the marks. And then we end up having 1 divided by the square root of x plus the square root of x, which is just equal to 1 plus 1 over 2 times the square root of x. And if you look carefully into this, our f prime of x now is just equal to 1 plus 1 over 2 root x. That's what we actually wanted. And now we want to find out now what is actually the domain of this function here. Domain of f prime is this. We have the square root here. For the square root to be defined, what is inside must be bigger or equal to 0. But because this is in the denominator, it must be bigger than 0. So this one, for it to be defined, x must be bigger than 0. Cannot be less because the square root will cancel it out. We'll actually say an error. So the domain of this is just saying that x is an element of real numbers such that x is greater than 0. Or you must say that a domain is just saying that we have 0 up to infinity. What this simply means is simply saying that f is differentiable on the open, okay, things right, on the open interval 0 to infinity. So because this one, the domain of this is actually this, so f is differentiable on that interval, or you can say it's differentiable on this, on its domain. And then let's look at the last one. The last one is simply saying that we have d. Our f of x now is equal to the absolute value of x, and we know that the absolute value of x is going to be x is greater than, it's going to be x if x is greater or equal to 0, and then we're going to have minus x if x is less than 0. Now, because we're actually having this whole thing here, it will be of good interest to notice something here. We don't really know what is actually happening at 0. Does the limit really exist at x is equal to 0? So we will end up having to actually have to find out what is happening at 0, because we have two things that are happening at 0. So we want to see if the limit actually does exist there. So what I want to say here is that whenever you have a piecewise function like this, always make sure that around that critical value you separate what you're actually doing and see if the function is differentiable or not. Now, what I'm going to do here, I'm going to say this. I'm going to split this into 3. I'm going to say that I'm going to take this out, equality, and say 0. if x is equal to 0, because it is 0. Right. Now, let us talk about, now we have three things, 1, 2, 3. So I'm gonna deal with this and deal with that and deal with that, and then we are done. So if x is less than, let me start with greater than. If x is greater than 0, what we're gonna do here, then choose h so that when I am taking x plus h, this is still greater than 0. So whatever the h that I am choosing here, I choose it so that whenever I'm adding that h in x, I still get something bigger than 0. Is this always possible? The answer is yes, because whenever you have two real numbers, if you have two real numbers, you are always guaranteed that as long as those two real numbers are different, there is always a real number in between the two. Even if you pick that number that is in between and the other number, the other real number, there is always another real number in between. So once you pick, even if you say you can pick 0,000000001, and then you pick a number that is different here, 0,0000002, there is another real number. In fact, there are so many real numbers in between these two numbers. So this one is always guaranteed. So we choose our h so that we still are actually operating in this same interval here, such that this happens. Then f prime of x under this condition is equal to the limit as x not x. Seems I'm the one who's going to get a 0 here. Please don't do the same mistake. It's going to be equal to f of x plus h minus f of x, and then divide by x by h here. And of course, in the value of x in this function here, I'm going to plug in x plus h here. So I still have the limit as x approaches 0 of absolute value of x plus h minus f of x, which is just the absolute value of x, all over h. Of course, this is the same as the limit as h approaches 0. And this one here, because this one is still bigger than 0, so I can always choose that this is still going to be x plus h, because if it is bigger than 0, I will still end up having that. So I'm still having this nice thing here, minus, I chose x to be bigger than 0, so this one is still going to be an x, and then I divide this by h here. Of course, this one here is actually going to be the limit as h approaches 0 of this x, and this x would cancel out, and now we'll end up having an x h over h, which is the same as the limit as h approaches 0, because this one and this one, they will cancel out and you're left with 1. And of course, the limit of a constant is that constant here. This function is actually differentiable everywhere. I mean, this one is actually defined everywhere. So if x is greater than 0, then f prime of x is differentiable everywhere. Right. So we know that at least we get something here that is differentiable. F is differentiable because, okay, I know this might be confusing you, because this function here, whereby you have y is equal to 1, its domain, the domain of this function is just x is an element of real numbers. So the domain of this here was supposed to be, therefore f prime of x is actually equal to 1 here. So this one here is saying that the domain is supposed to be x is an element of real numbers. So we cannot say that f is differentiable everywhere, whereas we actually chose this is the only case for x greater than 0. Yes, it is differentiable everywhere, but we still started with only this part here. So it is differentiable in this part. So this function is differentiable in that part. So that is why we are only picking that part out of this whole thing, because we don't know if f is differentiable when x is less than 0 or when it is 0. Now let's try and use something else now. If x is less than 0, we choose h so that x plus h is still less than 0. Now f prime of x is still going to be the limit as h approaches 0 of f of x plus h minus f of x, and then you divide this whole thing by h, and of course you still have the limit as h approaches 0 of this nice thing here. We have the absolute value of x plus h minus absolute value of x and all over h here. And if you look nice to this is just gonna be the same as the limit as h approaches 0 of this whole thing here, because x plus h is less than 0. So the absolute value when this thing that is less than 0, you always gonna multiply it by negative x plus h. Why? Because this one, if this is less than 0, I wanted the absolute value to be positive, so I need to multiply by a negative here, and then minus. If you look into this one here, when x is less than 0 here, I wanted to multiply this by a negative so that this thing here minus, I wanted to multiply this whole thing by a negative so that I get a positive value here. So for this one here, I will end up having a minus x and all over h here, which is the same as the limit as x as h approaches 0 of, if you look into this, I have minus x minus h, minus and a minus is a positive x all over h, and we have a minus here, you have a positive, so these two cancels out, and now you have a limit as h approaches 0 of minus h over h, which is the same as the limit as h approaches 0 of minus a 1. This h and this h will cancel, and the limit of a constant is just that constant there. So basically I have f, if x is less than 0, then f prime of x is just equal to minus 1. And now you know that this function is defined everywhere, so we can say that f prime of x is also differentiable when x is less than 0. Now we want to find out if x is actually 0. Is this function differentiable? Now we are looking at f prime. Let me use orange now. F prime of 0 is supposed to be the same as the limit as h approaches 0 of f of x plus h. But now we're looking not just an f of x, we're looking at 0 here, and then minus f of 0 all over h. This is very important here, because if you look into this function here, in this function here, 0 is somewhere this side, but when we want to approach 0 on the left, we will end up falling into this side here. So there is no way that we can just assume that to get this whole thing we can just take h as it is. So we have to look on the right of 0 first, and then we'll look on the left of 0 second. take note that f of x is equal to the absolute value of x is equal to x if x is bigger or equal to 0, and it is equal to minus x if x is less than 0. So when we are dealing on the right of 0, just picking a value on the right of 0, we are having a positive value, so we are actually falling in there. So this is going to be the same as the limit as h approaches 0 on the right of this. So I am going to plug in this whole thing in that function there. So I will end up having in the value of x here, I'm gonna plug in 0 plus h minus, I'm going to plug in a 0 here, I'm going to plug in a 0 here to get this f of 0 is 0 divided by h. So I end up having the limit as h approaches 0 of h over h. 0 and 0 are gone, and now we end up having the limit as h approaches 0 on the right of 1, which is actually just 1 because the limit of a constant is just that constant there. So the limit as h approaches 0 of f, or what am I doing now? So I have this on the right. Now I wanted to look now for the limit as x approaches as h approaches 0 on the left of f of 0 plus h minus f of 0 all over h. So what is actually going to happen here is actually this. If I pick a value just on the left of 0, so h is just a value on the left of 0, it doesn't matter what that is. We know that on the left of 0 we have a negative value, so we end up having the limit as h approaches as 0 on the left of this thing here. This one here, take note that the absolute value of x is just the same as x if x is greater or equal to 0, and then we have minus x if x is less than 0. So once you pick a value on the left of 0, it's going to be a negative value, so we are falling on it here. So this whole thing will need to be plugged in here. So I'll have minus times 0 plus h, and then minus, and then here I will end up having minus, and then I'm plugging in here this 0 here, or just 0, and then I divide by h. Of course, this is going to be the limit as h approaches 0 on the left of 0 is gone, so I end up having minus h over h, which is just the same as the limit as h approaches 0 on the left of negative 1. And now this is actually the same as actually minus 1. Now, since the limit as h approaches 0 on the left of f of 0 plus h minus f of 0 divided by h is not equal to the limit as h approaches 0 on the right of f of 0 plus h minus f of 0 all over h. Because this one is minus 1, that one was plus 1, we can say that f prime of 0 does not exist, or f is not differentiable at x is equal to 0. Therefore, f is differentiable on the interval. It is only differentiable on the interval of I have negative infinity up until you get to 0, but you don't touch 0, and also from 0 up to positive infinity, this interval. Or someone might say that when x is less than 0, or when x is bigger than 0, so we can have these intervals. That's when f is differentiable, but at 0 it's not differentiable because this limit and that limit are not the same, which means now the limit as h approaches 0 of f of 0 plus h minus f of 0 divided by h does not exist. So because this limit does not exist, it means that f is not differentiable at that particular point. Let us now do one last thing, which is much more important, more than anything that we actually have done so far, is I wanted to talk about one last theorem here, which says that this is the theorem. I want you to know it. Theorem. This theorem is saying that if f, the function f, is differentiable, right, at x is equal to a, then f is continuous. F is continuous at x is equal to a. So differentiability is more powerful than continuity. A function can be continuous but still not differentiable. Let's take an example here. If you noticed that when we had f of x is equal to the absolute value of x, you can see that this function is a function like this, right? And this function is continuous because I can draw it without lifting the pen up, so it is continuous. But at this point, it is actually not differentiable because f prime of x ended up giving us something weird, that when x is bigger than 0, where was it? When x is bigger than 0, the derivative was always equal to 1. So it was always equal to 1. So f prime of x was actually going this way. And when it was bigger than or equal to 0, so we had, this was shaded. And then when x was less than 0, we ended up having something like this. But at this point here, we started to have different values, so it was not differentiable at that particular point, because you can see that this is actually not there's actually a point of discontinuity there. We are not actually reaching to the same particular value, so the limit was not part of the limit was not the same at this point here. And then that's what was actually happening. So just because the function is continuous, it does not mean it is differentiable. But once the function is differentiable at that point A, it is guaranteed to be continuous at that point. We can prove it if you want to. Proof. I'm just gonna give a quick overview of this function, that this is actually true. So what we are actually going to do here is actually not that hard. So to prove that something is continuous, we know the conditions that right here for continuity. For continuity, we know that if you can prove that f of a is equal to some value L, and then you can prove that the limit as x approaches a of f of x exists, or the limit from the left and from the right is equal, and then thirdly, the limit as x approaches a of f of x is equal to f of a. Proving these conditions, you have proved continuity. But if I can prove this one thing, these two are also proved automatically. So I'm just gonna prove this whole thing here. So this is what we want to prove. So we want to prove this nice thing here. Now there is something that I want us to actually look at here. The first thing that I want us to look at here is the fact that I already have, let me change this. I already have f is differentiable. So I am suppose that f is differentiable, right? What does this simply mean? Note this one thing here. If this happens, then this happens. So I'm going to suppose that this is happening, and suppose that this happens, then the limit as x approaches a. Remember the definitions that we had here. We had several definitions that for a, suppose f is differentiable at x is equal to a. If that is the case, we know that f prime of a can be rewritten as the limit as h approaches 0 of f of a plus h minus f of a divided by h. So this one here is happening, it exists. Or f of a, remember this definition is the first principle. Now if we're using the old definition that we used when we were finding before the derivatives, that we're using when we are trying to find the slope of the tangent line, we can say that then the slope of the tangent line that is touching at a is supposed to be the same as the limit as x approaches a of f of x minus f of a divided by x minus a. So either this is going to happen or this is actually going to happen. So we wanted to prove that the limit as x approaches a of f of x is equal to that. So we are not going to use this definition here. We're only gonna use this one here because it is close to what we're looking for. So if this is happening, then this is actually happening. Now let us actually look into something here that is so much important. I'm gonna put a dot here and then go back to what we're saying. Now f of x minus f of a is the same as f of x minus f of a. That is true. And also I want you to notice that when we are picking x approaches a, this x is not the same as a, but it is a value that is so close to a, which means that when I'm dividing this by x minus a, this value is not 0, but because this one was not part of that, I needed to multiply by x minus a because it was not part of what we were actually doing. Right, it was not part of that. So this whole thing is equal to that, and this and that can cancel out, and I know that this is not 0, so I can always cancel out, divide and multiply. Now I am going to take the limit on both sides as x approaches a. Why am I using x approaches a? Is because I wanted to prove that this is true, so I wanted to use x approaches a here. Now that I'm actually doing here, I'm taking the limit throughout, so I will end up having f of x minus f of a, and this one here is actually going to be something like the limit as x approaches a of f of x minus f of a all over x minus a, and then times x minus a. That is what is nice here. And another thing that you can actually realize here, I'm going to take this thing as it is here. I still have the limit as x approaches a of f of x minus f of a, and then this whole thing here, you can see that I know that this limit exists because this one is actually the is actually the derivative. So I'm still going to take the limit as x approaches a of f of x minus f of a divided by x minus a times the limit as x approaches a of x minus a. The reason I'm doing that, I'm taking this as one function and this one as another function, so I can always split two limits. If this one exists and that one exists, it's always allowed. So I end up having the limit as x approaches a of f of x minus f of a. If you look into this carefully, you will find out actually that here we are actually having something that is actually so much interesting, that this one here, as we said before, that it is just f prime of a. So this part here, I am going to say it is just f prime of a times. If you look into this here, I have an x here, I have an a. So when I'm taking a value so close to a, when I'm actually plugging in a calculator, it's going to actually just round it off to a. So I'll end up having here an a minus a. So that I end up having something nice like the limit as x approaches a of f of x minus f of a is just equal to f prime of a times 0, which is just 0. So the limit, I can just say, as x approaches a of f of x minus f of a is just equal to 0. Now, we haven't proved what we wanted to prove here, but this is actually good. What we wanted to prove here is the limit as x approaches a of f of x must be equal to f of a. That's what we want to prove. But now, we haven't arrived there, but I know that this is the same as the limit as x approaches a of f of x plus f of a minus f of a. So I'm adding this and I'm subtracting that so that I can use that there. And if you look carefully into this, this is the same as the limit as x approaches a of f of x minus f of a plus f of a. And if you look carefully into this, this is going to be the limit as x approaches a of f of x minus f of a plus f of a. I'm going to take this as one function, and I'm also going to take that as another function there. So this one is going to be the same as the limit as x approaches a of f of x minus f of a. And then I'm going to add this. So because this is one function and this is one function, I'm adding, so I have to add the limits as x approaches a of f of a. So if you look into this here, you will find out actually that the limit as x approaches a of f of x minus f of a is 0. This is actually the same thing as that. So this simply means that I'm actually, this part here is 0 plus the limit as x approaches a of f of a. Now, looking into this limit here, you will find out that there is no x here. It's only f of a. So this relative to x is just a constant because there's nothing to plug. So that limit is just the same as f of a. Therefore, the limit as x approaches a of f of x, which was always on the left hand side, this one here, is actually the same as f of a. And we're actually done proving this whole thing. Can you see how easy this thing is? It's not that hard at all. Take notes of this, that we're actually doing the first principle. And the first principle was very nice in such a way that we managed to do as many things that as we can. And the only thing that I can say here as a preparation of of what we were supposed to do here is simply the fact that when is actually this function going to be differentiable and when is actually not differentiable. Those are also some of the things that you actually need to actually think of. So if you have a function here and your function is like this, you have a corner there. Can you see that you have a corner? So when you have a corner here, function is not differentiable at that point. So if this corner here belongs to some a, we know that not f is not differentiable at x is equal to a because you have a corner there. And then again, if let's say you have a nice function and you have a jump discontinuity at that particular point here, since you have a discontinuity, f is not differentiable. You get what I mean? And also another thing that you might end up looking at here is that if you have a function such that this function here, this point here is straight like this, and then it goes like this, such that if I were to place a tangent line at that point, it has to be vertical, it has to be straight vertically. So you have a vertical tangent at that point. At that particular point, f is not differentiable. So these are some of the points that you can look at. Look when you're actually having a corner, like we had with f of x is equal to the absolute value of x. You can see that we had a corner there. That is why it was not differentiable. And also at this point here, you know that it's not differentiable. And when you're actually having a function such that the tangent line is going to be a vertical tangent, then you can see that it's also not differentiable. These are some of the points. I hope that you understood the first principle, because next we will talk about the power rules and some of the basic differentiation rules that we can actually think of. Just take a look into this and then digest it, get some rest, and then get ready to some of the important things that are actually coming when it comes to the first principle. And also don't make a mistake of thinking that we are actually focusing on only the first principle. Just know that also these other functions, this one and that one and that one and this one, they also play a very good role in what we're actually doing here. Even when you are trying to approximate slopes, if you are given a table, you must know that information is still relevant and don't discard it. And a derivative, of course, is what you get from something else. That's what is important.